So you just watched a demonstration about Dalton's law of partial pressures, and you saw that when you have two different gases, oxygen that's produced and carbon dioxide, that the pressures of those two gases will combine together. They will add together to have a higher pressure. And so I'm going to show you the notes for Dalton's law of partial pressures and give you a few seconds to copy those down. And here are the rest. Okay. So on the video, the definition for Dalton's law of partial pressures, and you saw this in the demonstration, says the total pressure of a mixture of gases equals the sum of the partial pressures. So the oxygen gave a partial pressure, the carbon dioxide gave a partial pressure, and when you combined the two, they added. So mathematically, we can say that the total pressure equals the pressure of the first gas plus the partial pressure of the second gas plus the partial pressure of the third gas plus ... pressure to the nth gas. So we don't know how many we have, so we say that quantity is n. So also, in other words, if we were taking a look at the total pressure of the air, and we'll keep it simple with three gases, nitrogen, oxygen, and argon at STP, the pressure of the air equals the partial pressure of the nitrogen gas plus the partial pressure of the oxygen gas plus the partial pressure of argon gas. So at STP, 760 torr. Now these are values that have been found based on the percentages of these in the atmosphere. So the pressure of nitrogen is 514 torr, the pressure of oxygen is 242 torr, and the pressure of argon is 4 torr. You add those up, they add up to 760. Now the reason we need to talk about this, and this is going to be a bit of a twist on our gas laws, because the truth of the matter is we seldom have just one gas that we're looking at. The gases are not pure. They are actually mixtures. Just like in air. Air is just not one gas. It's a mixture of gases. When we do a reaction and they collect gases, they're often collected over water using water displacement. Now, in your book, they show the apparatus for this on page 255. And you see that they have a test tube there that they've done a reaction in. They're running a tube down through water and up into a collection bottle. And what they did is in that collection bottle, they filled it with water and they put it upside down in the water. And as the reaction goes, the gas will fill the top of the bottle and push the water down so that you are collecting the gas. The reason they do this is because if we just do a reaction and let it go, the gas will just go into the air. We have to have some way to trap it. And the way to trap it is through this method of water displacement. We can trap it above the water. Now, during this process that's shown on page 255, so go take a look at that, some water vapor mixes with the gas. There is always some water evaporating up into that bottle along with the gas that's produced. So for calculations, we want only the pressure of the collected gas. So we must subtract the vapor pressure of the water from the atmospheric pressure. These values are found in table 10.4 on page 256 of your book. So what is vapor pressure? Vapor pressure is the pressure exerted by a vapor or gas in equilibrium with its solid or liquid state at a specified temperature. So when a gas evaporates, it's pushing up against the atmosphere with a certain pressure, okay, and it escapes. And this is an equilibrium process. There's water evaporating, there's water also condensing back and forth on that surface. Now, I'm going to take a look at this chart. So let's turn to page 256 in your book. Should have had this ready, but I didn't. So hold on just a second. Okay, so page 256. Here is the table. And I see the temperatures. They give you the vapor pressure in torrs and in kilopascals. So you can choose which you need to use. And we can see that as the temperature goes up, the vapor pressure goes up. Okay, so you will see that trend until, and this is going up to 100 degrees Celsius. What happens at 100 degrees Celsius? Water boils. And so we see that at 100 degrees Celsius, the vapor pressure is 760 torr. Well, that is atmospheric pressure at STP. And the reason for this is the vapor pressure of water at 100 degrees Celsius is 760 torr because to boil, it must push up as hard as the atmosphere pushes down. So that's the reason for that value. And this is also why if the pressure changes, the boiling point will change. If atmospheric pressure changes and fluctuates, if you have a lower atmospheric pressure, it boils at a lower temperature. This is the reason that salt must be added or things must be cooked longer at higher elevations because you need to either cook something longer to get it fully cooked or you need to raise the boiling temperature. And that's what adding salt and things will do. We'll talk about that when we talk about solutions. And so that is an important thing to know. All right, so let's do a problem. So I'll put this problem here, give you a few seconds to write that down. Here to turn off your video and write it down while I prepare my answer here. Okay, so a 46 milliliter sample of oxygen gas is collected over water at 25 degrees Celsius when the atmospheric pressure is 102 kilopascals. What volume of pure oxygen is this at STP? So this is a two-step problem. Well, yeah, somewhat. Okay, there's going to be a couple of steps here. You know how we always convert the temperature to Kelvin? Well, here we're also going to have to work with the pressure and the table on page 256 before we can use our combined gas law equation. So P1, V1, T1. So looking at my problem, my original pressure, 102 kilopascals. Now this is collected over water at 25 degrees Celsius. So I have to go to my chart on page 256. I go down to 25 degrees. So right here, 25 degrees. I'm after kilopascals, so 3.167 is what I'm going to subtract by. And when I subtract, I get 98.8 kilopascals. Okay. My original volume is 46 milliliters. And my temperature is 25 degrees Celsius. Convert that to Kelvin. And I get 298 Kelvin. All right, I'm gonna write my other set of values over here. So P2, V2, and T2. I want to know the volume, so question mark for volume, at STP. So pressure at STP is 101.3 kilopascals. And for temperature, it's 273 Kelvin. Remember, this you'll find under the STP section in your notes, okay? If you don't remember. Write down my equation. Plug in my numbers. Okay, now to solve for V2, I am going to cross multiply. And to get V2 by itself, I'm going to divide both sides by these two numbers here. That all cancels out over there. Cancel out my units over here. I'm left with milliliters, so I'm good with volume. V2 equals, when I multiply these numbers on the top and then divide them by these numbers multiplied on the bottom, I get an answer of 41 milliliters. Now, why two significant digits? Because I have two significant digits here, so I can only have two in my answer. Okay, let's go to page 257, number 7. Page 257, number 7. So go ahead, take a look at that problem, try it on your own. Here is the answer. I think I can get it all on there. There you go. So if you got this answer, you can just stop here. If not, I am going to walk you through how to do this. Okay, so page 257, number 7. When I read my problem, it says a sample of 40 milliliters of hydrogen is collected by water displacement at a temperature of 20 degrees Celsius. The barometer reads 751 torr. What is the volume of the hydrogen at STP? So I write down my quantities that I know. My pressure, volume, and temperature, V1, P1, V1, and T1. My original pressure is 751 torr, right? Yep. 751 torr. I think I accidentally wrote 750 torr on my original problem over there. So I copied that down wrong by accident. But what we have to realize with this is the pressure of the hydrogen plus the pressure of the water. Okay, so we have to subtract the vapor pressure of the water from this in order to have just the pressure of the hydrogen. So this is at a temperature of 20 degrees Celsius, 293 K. So at 20 degrees Celsius, I go to my chart on page 256. 20 degrees Celsius, the vapor pressure of water is 17.535. And this is the pressure of the water. So the partial pressure of my hydrogen is subtracting those two. Let me make sure my answer that I did write down was correct here. Yes, I just copied that wrong. So 733 torr. Now I'm dropping the decimals because remember the rule for addition and subtraction is we go with the lowest number of decimal places. So that's why I dropped these decimals, because this is only at the ones place. My volume is 40 milliliters. And my other values, P2, V2, and T2. They give me that this is at STP. So I'm looking for volume. Pressure is 760 torr. And temperature is 273 Kelvin. Write down my equation. Plug in my numbers. Remember, my corrected pressure here is what I use. My values for the other side of the equation. Cross multiply. And then to get V2 by itself, divide both sides by these two quantities here. These all cancel out. Cancel out my units over here. I'm left with milliliters, which is volume, so that's good. Okay, so V2, when I multiply across the top, divide by what is on the bottom, I end up with 35.9 milliliters. 3 significant digits because all of the numbers up here are 3 significant digits. Okay, I am going to stop here and I will do the homework problems in a separate video. But the homework is page 272 to 273, numbers 18 and 20.